Think you guys ready to go? You think you can take one more lecture? I know it's pretty hard, but this will be lighter weight than Benjamin, Amal, or Steve. So I'm not going to try to get through a deep theorem on categories or even on protocols. Here I'm reminding myself on the first overhead that if you want to read about any of the type theory concepts, we have a lot of online books that are describing theorems proved in New Perl and actually all the concepts that you need in the type theory. There's a book by Stuart Allen there. It's a web book. You just read it and click around and follow definition chains. So for any concepts that we're using here that you want to know about, you can just go read that book online. Plus, we have a lot of examples of mathematics presented in the computational constructive type theory there, but not so much from this lecture. So as I say, this one it's going to have a different character to it than the one where I was proving a completeness theorem and all that. So basically, since around the mid-90s, the Perl group and many others around, especially in Europe, were trying to extend this program extraction paradigm to processes. And we had this slogan, proofs as processes. And it was motivated by the fact that proofs as programs was working so well, especially you're going to hear from Xavier Leroy later in the school about his extraction of a compiler, right? A C compiler from code. So people were thinking, wow, you can do just about anything. Let's go after the really hard stuff like operating systems and all that. So the goal is to create correct by construction protocols or components of operating systems from constructive proofs that the specs are realizable. But to do this, you need a whole new machinery. We need a theory of concurrency and protocols. In the case I'm going to talk about here of distributed computing. Now, it's a pretty natural goal, and one of the first papers on this was by Samson Abramsky in 1994. I remember that paper very well because I was the session chair for his presentation, and I was sitting right in the front row, but this topic was so fascinating to me that I lost all track of time, and Samson was noticing that the front row was really into this, so it's going on, and all of a sudden somebody yells out from the back of the room, "Who's the session chair anyway?" And I woke up, oh my God, I'm the session chair. Oh my God, he's 15 minutes over. So it's a heck of an interesting thing. However, this was done using linear logic at the time when Jean-Yves was also saying this is the solution to all your problems. Here, just use linear logic. And also process algebras were part of this, and Robin Milner got very interested in Abramsky's talk and tried to use process algebra to do this. But the long and the short, after seeing many, many papers on this from very talented computer scientists, nobody could extract a distributed protocol. Nor can we extract components of an operating system, even though the group in New Zealand did the SEL4 operating system kernel that they verified in HOL, but nobody's been able to extract these protocols until now. We just did this last week. We have a running version of multi-paxos and simple consensus running in a database system, a replicated database used at Cornell, and it is going to be the database for the interactive development environment of New Perl. So we cared very much about it being right, and it did take us probably 10 years to actually get this. I'll just tell you the highlights of the story and some of the really interesting ideas that have come out that are, I think, worth knowing here. So why is this work important? Well, Vincent Raleigh, who's on the team there, did I mention the group? I will mention the group in a minute. So Vincent Raleigh, our postdoc, just gave a talk on this Paxos extraction in Germany, and his motivating slide was just this: problem, unverified protocols are wrong. And this is a lesson we've learned the hard way. You cannot get these right, and I have a protocol in here that I took off of Wikipedia, and I'm not sure it's right. We'll see. But our experience is they are wrong. They're all wrong. And there's something very bizarre about this. We knew this early on when we started trying to verify protocols. That's a different story, right? Not synthesizing, but just verifying them. And people have been doing that for a long time and discovering gradually that all the unverified ones are wrong. And indeed, John Mitchell made a whole master's course out of this by saying at the beginning of his master's course, your project is to find a protocol newly published and find the mistake using some of the tools in the course. And the students inevitably said, but what if there's no mistake, Professor Mitchell? And he said, I've been teaching this course, the last time he did it, said this, for 10 years now, and it's never failed. So they're just all wrong. And we were in the business of working with a systems group for many, many years and trusting them a lot. And one time we were verifying one of their protocols, and we found a mistake in it. They'd been running it in their deployed system for something like 7 or 8 years, and they didn't believe us. They said that couldn't possibly be a mistake. They said, kind of in parentheses, we're the best in the world at this, and they probably are, and we've been running this protocol for a long time, and it's right. So we just used NuPearl to do the trace. Here's what goes wrong, and then we showed it to them. They asked for a day to think about it, and then I heard Berman, the leader of the group, out in the hall saying something I didn't mind hearing, but I had to correct. He said, you know, Constable's a genius. He found a mistake in a protocol we've been running for years. We're the best guys. So unfortunately, I had to tell him, Ken, I didn't find it. NuPearl found it. So anyway, they're wrong. They're almost all wrong. And I made a personal $1,000 bet against someone who told me they had verified a protocol we've been working on. I said, I'll bet you right now, on the spot, $1,000. If you haven't verified it, it's wrong. And they wouldn't take the bet. So I'm kind of glad they didn't take the bet because I didn't have $1,000 at that moment. But so here's the other part of the problem, though, that these protocols are part of the world's critical IT infrastructure, right? They are running cloud computing, and as I mentioned in the first lecture, the reason the military doesn't want to move its resources into the cloud is they can't trust anything there. But now we have cyber physical systems. That's things that will drive your cars and run the predators that are watching over, trying to watch for speeders and whatever else they're going to do. But the things driving your car, they now know that if you can just insert a DVD player into the Cadillac Esplanade or one of these, all you have to do is insert a specially created, corrupted CD into the disc player there, and you can take over the entire car while it's driving. You can accelerate it, you can slam on the brakes, you can turn the steering wheel. So it's a pretty scary thing that the protocols doing all that are distributed protocols, and they're probably all wrong. Okay, so anyway, we've been trying for a long time to deal with this, and we've been working all along hand in hand with the Cornell Systems Group, Robert Van Renesse, Ken Berman, Nicholas Schipper. And we did some early work with Mark Hayden, Jason Hickey, Christoph Kreitz, Chet Murthy, And we actually got an SOSP paper out of that work. And you can only get into SOSP if you've somehow sped up a system a lot, right? And with formal methods, we sped up one of their systems by a factor of 50. So they like that. And then we have the formal methods guys working on this. There's Vincent. So the question is, how do you think about this topic? What can we do here? We're not experts. We're not like Ken Berman, Robert, Vincent, who've spent years building these systems. So how can we get into this? What's our role in this? And just for laughs, how many of you have ever written a distributed protocol? Even in a class, homework? Oh, yes. So put them there, I know. Okay, good. Is it anyone written one in a deployed cyber-physical system? Yeah, probably not. But, okay, but even if you haven't, we can still deal with some of this. I think there are interesting issues for programming languages. There are connections to logic, deep connections. And I think we, in this room, even though we haven't written a lot of distributed protocols, we will be able to contribute to getting this right, because first you need a logic to reason about things. We're going to need to formalize these protocols, and we're going to need the right logic. Now, this topic has already been fun for me because one of the participants, Heath Putnam, was back there. He's actually in this business. And we were talking about why can't people get the protocols right? What is wrong with us? And it's partly, there's something wrong with our brains just are not set up to think in the way that these protocols interact. Many, many things going on at once, right? Certainly, the only ones among us who have a chance are the women, right? Men, at least my partner tells me, we can only think about one thing at a time, and we're sequential creatures. And when I watch what she does compared to what I do, I think, yeah, that's true. So there aren't enough women here to solve this problem, so we better get some more. But Heath was saying something yesterday when we were chatting about this per chance at a coffee shop, that humans are pretty good collectively at making good consensus decisions. We can figure things out. The whole crowd will figure out what to do. So collectively, we're pretty interesting there as a species. Okay, so now there are various views about this, various approaches. One of my colleagues, Joe Halperin, loves this area. He's done a lot of work on protocols, but he loves it because of its logic puzzles. So he's always doing these puzzles about how do we achieve common knowledge. You know, if you've got children with somebody has mud on their forehead and you want to know who it is, it takes many rounds to figure this out. All these cute problems he can solve, but he admits in his papers, at the end of most of his papers, he says, that's a cute logic puzzle. It doesn't seem to have much to do with the internet. So you can do that. You can look at these as logic puzzles. You could also try to explain, as Heath and I were doing, why the human mind can't do it. But there's something better to do here, I think, and that is creating the logic. So a theory that accounts for protocols and processes is going to be a very interesting computer science theory because it's going to deal with the real world in the way programming language, the way programs don't. These protocols have to interact with the world, with what's happening, with sensors, with other computers. So I think the theories that we create here are going to be the computer science analog of relativity theory and quantum mechanics. First of all, there is relativity theory. The notion of time in these distributed systems comes directly from Leslie Lamport's education as a physicist. And in his paper on causal order, he says, I got all these ideas from studying relativity theory. So it's going to be relativity theory, but we're going to have to make that merge with quantum mechanics, because the other thing about these protocols is that they're uncertain. They're working in an uncertain world. and you don't know whether they're hung up, whether they're dead, whether they're ever going to respond to you again. So the theories that we produce here are going to be, I think, among our most complicated and interesting and sophisticated theories. Okay, so, all right, and here's the reason. Oh, I thought I had to have one sensible reason for you guys. I believe in all those reasons, but many of you are probably saying, well, he's becoming a philosopher here. But actually, what I think is going to happen is that our proof assistants are, for constructive type theory, are going to be running in the cloud. We are going to have to put them there because we need the computing resources available. So I know new pearls go in there because in verifying these protocols, we sometimes have tactics that run for 2 days. We've got the thing set up, we know it's going to work, we say just let it run, and it runs with all of our 30 processes on it. Well, we save one for everybody who's working. You have to reserve your process. All the rest, 25, they're working on this problem. But we're just waiting for the day, which is coming soon, when we're going to deploy 100 and then 1,000 processes on the provers. And if we do it, there'll be competition. Other people will get into the game because it's going to give us an edge in getting DARPA contracts. And as soon as you have that edge, everybody says, well, so COC, I can guarantee you, they want to play with DARPA. If we go into the cloud, they're going into the cloud. But once we're up there, or in there, we're going to have all kinds of issues. And Andrew Myers will talk to you about the security issues. How do we know people aren't planting false theorems in the database to throw off a competing verification team? How do we coordinate all these running protocols with running processes with protocols that we know will work? So I predict we're going to be there, we're going to be in the cloud, and we're going to have to apply all the methods you're learning to make sure that this works. And the logic of this stuff is going to be really deep, in my opinion. Okay, so here's the plan. I'll present our logic of events. It's the logic we think is the right way to go about this. And then I'll discuss a little bit the synthesis methodology that's worked. But then I'll present a new theoretical idea. And even though it's a new piece of theory, it's kind of fun and it's lightweight. It's not as heavy as category theory, nor as heavy as proofs about data structures. It's got about a 3-page proof. So we'll do that at the end. Okay, so the logic of events is a theory of real-world distributed computing. And it's a scientific theory presented then in a constructive type theory. And in the first paper we wrote about that, we wrote one sentence, Mark Bickford and I, and we said, possibly this theory will have some value in explaining the paradoxes of quantum mechanics. And sure enough, somebody found that, Alan Bundy, and he wrote a proposal to study this aspect of the theory. So it may not be so wild what I said about relativity and all that. Alan Bundy has a group studying what you can say about physics with languages like this. Okay, but our language came in a different way. We have to work with the systems guys. We do not understand what protocols are important. We don't know how to begin to reason about them. So and they're very busy at what they do, so we couldn't tell them, how about you use the pi calculus to do this? Or how about you use temporal logic? We had to listen to them. What do you do? How do you talk? And they didn't talk temporal logic. They didn't talk process algebras. But they did talk a language that we could formalize. They talk in things called message sequence diagrams. And here, I haven't done anything at the board. I'll draw. You can tell when you're walking into the office of a distributed systems guy, because they've got diagrams like this on the board where they're talking about, okay, these two processes over here, P1 and P2, they just sent a message there, but They're also sending over here to this guy as a backup. So they're drawing diagrams like this. And those diagrams are explaining how the protocols communicate with each other. And you can almost for sure spot who in your department is in distributed systems by looking at the blackboards or whiteboards as you go down the hall. If they got those on the board, those are the distributed systems guys. So the theory should start with that, with events in space-time. So our model is that thing there where you've got addressable locations. Here are only 6, but typically there are dozens, maybe hundreds. And what's happening at each one of those locations, say, let's take location 1, you've got a bunch of events showing up there as circles, and you also have events where they're sending, like 1 just sent a message over to 2 when it came alive. So that's what's going on. That's what those arrows are telling you. But a very interesting thing motivates the reason they do this. At every one of those addressable locations, locus of events, the circled events there are occurring sequentially. So you've got this idea that Tony Hoare also realized was a very important thing in reasoning about distributed systems. You've got these loci of sequential behavior. So he called his thing a calculus of communicating sequential processes. The individual processes are working sequentially. Things happen there in linear order. But the actual order in the world is determined by looking at the predecessor relation at any one location and also at the ordering of messages that were sent to you. So you want to trace back, say this guy will trace back, say, all right, this is a predecessor of that message. There's a predecessor of the one locally. This guy way over there, he's a predecessor. So you calculate backwards you take the transitive closure of the local predecessor and the send predecessor relation. And that gives you what Lamport called causal order. That's time in the distributed system. And there is like an event cone. For any event here that you pick, you can work backwards and find all the prior messages in causal order. Okay, so there's no other notion of time. You can't say that at location 1 and location 6, 2 things happened at the same time. First of all, 1 might be a rocket. 6 might be zooming off into space with a different clock or something. There is just no local notion of time, no absolute notion of time beyond this causal order. Okay, so there I'm just summarizing what I said. The basic references for us on this were Lamport's paper, Time Clocks and the Ordering of Events, way back in 1978, and a PhD thesis written by Glyn Winskill at Edinburgh in 1980 on a logic of events or an event structure for Petri nets. So those are the 2 bits of prior work that we depended on. So now, once you've got this model in mind, what we want to do is bring it into type theory. So the first thing we do is introduce the type of events. So this E there is the type of events that are occurring in a world like that. Every one of them has a location. So that's another type. And there's going to be a function that gives you the predecessor of an event at a location. So you can say the predecessor event. So if you've received an event at a location, you can ask, well, where did it come from? Was it a message sent to me, or is it the local predecessor? And the way we have this thing bottom out is that it ends with the location. So you can always find the originating location there of this chain. Okay, so you've got operations like that. I'll show you more of them, but I don't want to overwhelm you with the structure of this theory. I'll just show a couple of the axioms that you can put down for this little tiny piece. You can say something like, for any event that emits a signal, we can find an event E prime by which it's received. Now that's an assumption that you may not have for a lot of protocols, and you can always arrange so that that thing at which it's received is not the sender of the protocol. So if you've got a link between yourself and someone else, and you want to model that as an unreliable link, we just plant somebody in the middle who swallows up messages from time to time. So the message is received by someone, but maybe not the intended receiver. Okay, so then you have this axiom that the predecessor function is one-to-one, and the axiom that the Lamport causal order is strongly well-founded. And I'm just going to leave that as an axiom at the moment. So what we do is we start with this little thing that I just described there, events with order. And then depending on the application, you may need a lot more structure. So for example, you might have a communication topology where you need e-communication, and you talk about how the various locations are linked to each other. Is there a direct link between 1 and 2, or do we have to send the messages by routers and so forth? So I won't talk much about that. Also, there's the value, events with value, e-value. You have to talk about what kinds of values do events have. But there's, in general, all the events will have values, so you have this operator here, value of the event. And then when you get to talking about the state at events, you're going to introduce a temporal logic where you can say, okay, at a particular state, we might know a property initially. We also might know a property when an event happens. We might know that when an event happens, the receiver is actually waiting for it. So there is going to be a temporal logic that's derived from this. Okay, so there, for example, is a topology of a network where we've got particular links between the nodes. So there are links back and forth between 1 and 2, between 2 and 5, and so forth. I think looks like that's completely connected there. So yeah, here you have a completely connected topology. Okay, so now let's take an incredibly simple example here and show how we could synthesize a two-phase handshake protocol between a sender and a receiver event. There they are, S and R, and they have these links between them. So S can send to R on this dedicated link, and R can send back. And we can describe now the events E that have a location P, so that's E sub P. We can then describe the events at S and the events at R. We can talk about the events that sent from P to the destination on L, and so forth. So here's what we would like to prove, a really simple thing. We want to say that if that before the sender sends another message to the receiver, it should get an acknowledgement so that we're not going to overwhelm the receiver and fill up the buffers. So you want to say, okay, we're going to arrange for this particular problem that if you've got two events, E1 and E2, that are send events from S over to R on link L1, then there has to be a receive event over there at S that sits between E1 and E2. And that receive event, actually, you can tell by the structure of it, it came from L2. Yeah, so here we see in the diagram. So you've got a send over to R, and then the receiver acknowledged, and we've got this event R here that comes between the event E1 and the event E2, the send events. So how can we guarantee this? So first of all, notice there is a clean specification. No there's hardly anything except ordinary first-order logic. In fact, you can do most of the examples I'll talk about now in first-order logic. So that seems clean, right? Simple, easy to understand. Much easier than the category theory, right? I mean, here, just quantifiers and and you can imagine you're probably, some of you are doing this already. You're sending messages there and hoping for answers. Okay, so now we want to have a theorem like this that says, all right, for every E1 and E2 send events from S, where E1 comes before E2, there is going to be a receive event between them. And we want to guarantee that property and prove a theorem from which we can extract the protocol that will be the send protocol. Okay, in order to do this, we understand, well, by just thinking about it a bit, we realize we should have some part of the state there at the sender called a ready. And we send, but before we send events, or send messages over to S, we want to make sure that the process is ready to do that. So we'll say that we require ready to be a true variable when a send event occurs, and we can require ready to be false after it was sent. So now you see how this protocol is going to work, right? So you set the ready predicate to be true when you want to send. As soon as you receive a message, you're going to set it to false, so it can't send again. All right, so there's the fairly trivial idea, and now you can prove some lemmas. The point here is just to show you that we can reason about this stuff and actually do some synthesis. Okay, so here's a lemma. We're going to say for every send event at S along the link L, ready after the send is false. We're going to need that fact. In lemma 2, we'll say S sends on a link only when ready is true. So for every event E that's a send, ready when the sent happened was true. Yeah.
Should we interpret after as just one step in the normal temporal logic interpretation?
Well, so remember, at all these locations, you have, if there was a send event, then there'll be, that event will be there, a dot, say, in that location. And after will be any of the events that occur after that.
So then that would say that it's always not going to be ready afterwards.
Right. Well, until, so we also had this condition, now we're going to have a condition that says that sender better be able to it must have a way to reset ready to true. So you know, after that, immediately after that send event, that's what this thing is saying, after the...
That's what I'm saying, immediately after or indefinitely.
Oh, not indefinite, no. So after that event was sent, we know that unless some event changes the state there, that ready variable will be false. But we can now change it. That's just saying, okay, after that event, I know ready is false, but I'm going to need it to be true somehow or other. So how are we going to do that? Well, here in 3, we'll say after S sends on a link, it's ready only after it gets an acknowledgement. So we can have a theorem here that says for every send event, E changes ready to true implies that E was a receive from its partner in the message passing. So we can put a condition down here that tells you when it's going to change. Yeah.
I thought you said that there was some uncertainty about when things are going to come back or not. So what if an acknowledgement never comes back?
Yeah. Yeah, so if there's failure here, but we're not, so the process we're looking at now isn't going to fail. We don't put any assumptions in. So as long as nothing fails in the protocol, these conditions are going to happen. Now you could invalidate the whole thing by saying, well, the process might just stop. And then there'll be none of these other events that you can talk about. If it dies, now there are no more events happening. But if there are these other events, here are the conditions we know about what's going on. Okay, so now you can see the notion is these are just invariants about the way we want the thing to be designed, right? These are properties. We'd like to say we want to design protocols at S and R that have these properties. And I'm looking right now just at the sender. So we want to make sure that we can guarantee, as long as the thing is up and alive and running, that after the send event, so you've got a send event E there, ready is going to be false. So that's all I know. Sometime after, not always, but after that event, it will be false. Now I need some kind of event here, if he's ever going to send again, to set that ready back to true. And how do and we know intuitively what we want to do, but I don't want it to be intuitive. I want the logic to tell us what to do. So here in L3, we say, after S sends on link L, it's ready, again, only after a receive message comes back on the return link. Right? So that's a condition. That we're saying that's what is going to have to happen if this protocol satisfies, if we can find a protocol that satisfies these conditions. Yeah.
Where after some time, without the acknowledgement, then you retry to send the message?
Yeah, well, good. It wouldn't be this one, though. You can see this guy isn't going to be able to do that. So there is already a deduction you can make. If we've built the protocol to satisfy these specs, it won't be that. So here we're already doing some collective reasoning after less than 10 minutes on using the logic, right? We're saying, if that's how I specified it, it can't be one of those kinds of protocols. Okay, but it's, this is enough to tell us what the protocol is going to be. So now we establish a theorem like this, and this is in one of the papers we wrote on it that I cited, so I won't spend a lot of time on it, but here's the theorem. It says we can prove that, we want to prove that given any two send events from S to the receiver, there will exist a receive event between them. So how do we do it? Very intuitively, if you've got two of these, so you look at E1. At that send event, ready had to be set false. So before it could send again, it had to have some kind of event that allowed ready to be reset to true. But our lemmas here said the only way you can do that in lemma 3 was if you got a receive from the other guy. So here already the reasoning is pretty clear. You had to have a receive event occurring over there at S before you could set the variable to true. Okay, so it's trivial, no doubt about that. And there's the proof. You know, I'll hand out these slides. But you can now, there's too much proof for a trivial predicate like this, but it shows why this business is tedious. Here's the machine we get out of that. We can actually show that these statements I just gave you are realizable by a process model that has the capability of setting variables and sending messages. And here is the little process automaton that comes out. But it needs one other cool thing. It needs what we call the frame condition there on this automaton. And it says only receive events and the send events can affect this ready variable. So here, that last line, we talk about, this is called a frame condition, and it says just the send and that receive can change this variable. So you've isolated what you have to say about it. But that little machine there is a piece of code. I won't, I'll have to be careful here not to go into too many more of these. I'll give you one more real quick one. Here's Here's a fairly sophisticated process. That was trivial. The next thing we did was go after something in the distributed systems literature that wasn't trivial. And we have Peterson's leader election in a ring. It's a very cool protocol. These processes are all hooked together in a ring that they can send messages to each other here in this clockwise ordering on the special links. And what happens is they want to elect a leader, somebody that is the process the outside world will contact when they want this group to do things. So there's an incredibly elegant algorithm for this if every one of those processes has a unique object identifier. If you can say what your identifier is, and these identifiers are numbers, natural numbers, then the way the leader election protocol works is everybody sends their ID to their neighbor. They have one unique neighbor, right? The thing to their clockwise direction. So you send your UID along, and the process gets that and compares it to its own ID. It says, all right, if this ID that came in is bigger than mine, I'll forward it along. If it isn't, I won't forward it. So you can pretty easily and intuitively see that this process will elect a leader in the following way. Only one of these guys is going to get its own UID back, right? Only the maximum ID. Any other ID will get trapped by someone who's smaller. So you know that if nobody fails here, and we're assuming that, this process will elect the leader with the maximum UID. And it's not so hard to prove that. There's a theorem. We write down the theorem for it. We prove some properties like these lemmas. And you know, they're not all that hard. I've taught these to undergrads. And out comes a leader election message automaton. This is a piece of code that was synthesized from the proof that you could do this, that the leader election thing will work. So there it is. That's actually synthesized in a language that MIT was in a variant of their IO automata language, which our systems guys liked, and they were using this as one of their models. So we showed them how we could synthesize protocols. Now these are trivial protocols. That's just to get our machinery up and running and to make sure that we could deal with reasonable protocols. Okay, but now what are we doing here? I said we're going to, oh yes. So we're going to illustrate something that we're working on right at the moment with a protocol that is also very, very simple, like this leader election. But this protocol, I think it's only 4 lines long. We'll see in a minute. This is one that people get wrong all the time, and I might have gotten it wrong. We'll see. I was worried as I'm walking over here. I thought, oh dear. I took the protocol I'm going to show you off of Wikipedia, and then I changed it because I didn't like the wiki one, and now I'm not sure the change is right. I think the wiki one is right, but there's no guarantee. My colleague Fred Schneider says, you pick this algorithm, look it up in the book somewhere, and the chances are it's wrong in the textbooks. So I thought, okay, wiki, that's a good place. But this one looked right to me. The Wikipedia algorithm looks right. Okay, so what is the Peterson algorithm trying to do? There's the wiki code, but let's explain what we're trying to do in terms of this diagram here. This is a shared memory algorithm where these two processes, P1 and P2, I should have called them P0. I did this before I looked in the wiki, and they call them P0 and P1. I forgot to change that. Okay. They're trying to reach a critical section. Say they're trying to write or trying to get a printer or something like this, or to get a hold of an element in a database, or write to some object in a database. And that's called the critical section because you want only one process at a time in there doing whatever it's supposed to do. So in order to agree who gets to go, the protocols have use 3 variables. This A1 for that P1 can write to, but P2 can only read, and A2, a variable that P2 can write to, but A2 can only read. And those are the variables that are going to tell each other whether they're interested in getting in the critical section. And then there's the turn variable that says whose turn it is. And both P1 and P2 can write to turn, and they can read it. And the idea of the protocol is this. If you want to go in and get to the critical section in your P1, you set A1 to true. You say, I want to enter the critical section. You also check to see whether A2 is set to true. And if it is, you say, oops, I'm in a race. The other guy wants it too. We both want it. So I've got to, as fast as I can, get to the turn variable there and set it. And now you think you might set it for yourself, but you don't. You set it for the other guy. So you rush to the turn variable and set it for that process. So you set it for 2. And that protocol, if nobody dies, again here we're assuming everybody is alive, this is the wiki code where I didn't initialize both bits of it here. So they initialize their, say P0 initializes its flag. That's its A1 thing. And it initializes turn. And then it checks to see whether, so it's now going to look at the flag there to see whether it's true. It should be looking at the flag of the other guy. Okay, so that's probably, shucks, I hope I didn't just make a typo there. No, but you have to, so at P0, he's got to look at the flag of, okay. So, sorry, P0 sets his own flag to true, that's right. So now here, and he sets his, if he wants to go in, he sets his turn to the other guy. And now he does this check. While the flag of the other guy is true, well, it still wants to go in, and the turn is 1, you're going to sit there waiting. But if the turn ends up to be you can go in. So why is that? What's the intuition? Well, when you wanted to go in, you set the other guy's number into turn. So if when you look at it, you see that the turn is actually number 1, that means he got in there and reset the variable after you set it, right? You set it to him. He set it to you. So when you look at that, you say, I beat him. I got there first, and he reset to me, and that gives me permission to enter. So now you go in, you do your thing, and when you come out, you reset your flag defaults. Okay, so that's what you'll see on the wiki page. That's the code. There it is again with key variables listed. And you should be able to think about this yourself. It's not that hard a protocol. But you have to be able to prove the following 2 things about it. You should be able to show mutual exclusion, that it's never possible for both processes to be in the protocol at the same time. So why is that true? Do we see intuitively why they can't both be in there? So the one that got in there, that went in because the turn was set to his value. So the other guy can't have entered because he doesn't have the turn in his favor. Okay, so that part is pretty clear. And the other thing you have to guarantee about this protocol is that nobody gets starved. PI can't just sit there running back in, getting the critical section, then coming out and going right back in again. So you can't starve out the other process. How do you know that can't happen? Well, when the process that's in there finishes, it has to reset its weighting. It has to say, I'm not waiting anymore. So if the other process is now polling on that wait, which is what it's doing, it can then enter. So there's the argument. Now you might think, this is not too bad. It probably isn't too bad. I think we've got it close to right. But, okay, this is more description of it. And this is I'm not going to show you my optimization. I thought, well, you can optimize this code a little bit. If you find that the other process is not waiting, you might as well not race for the turn. Just go in. You look, you see nobody wants it, so why should I bother setting that other variable? I'll just go in. And I think this is right, but I'm not sure. You could check for bugs in that. Okay, so now, and that's what I just said about the argument. So now this looks like it's very amenable to the logic of events. So we can write down the conditions in terms of the event logic you've already seen for when a process is allowed, say when two processes are contending. And that's a good exercise that I'm assigning here. You could describe, now just using this event language that you've already seen, when is it, what kinds of events or properties of these variables at events show that the processes are contending? So you want to think about that and write down an answer. And then another exercise is describe the requirement for some process to have gotten in there. So for one to be in the critical section, what do we know? And you'll find this isn't too bad, I hope. And I'll be happy to answer those exercises tomorrow. Think about them. But here's the problem. So this seems like a nice protocol. You can almost understand this. But our systems guys refuse to use shared memory. They say this is too dangerous. We won't use it. The Microsoft guys don't use it. People don't use it. And the one reason they don't use it, Lamport wrote a whole paper about why you shouldn't use this kind of thing, and he wrote an algorithm called the bakery algorithm to do it instead. And here's the problem. It depends too much on the hardware. So you're racing for this turn variable. You go in there, and you might actually be reaching it at the same time as the other process. So you're both trying to write on it, and who knows what's going to come out, what's going to happen. So you have to have all these conditions on the registers at your machine. They have to be safe registers, or this kind of register, or that kind of register. And the distributed systems guys don't want to count on that. They say it's just too tricky, too difficult. So here we are, liking shared memory. We think this is the way to deal with Peterson, and they tell us, no way. We're not going to, you can write all those protocols and verify them as much as you want. We won't use them in the system. So we're scratching our heads, saying, well, shucks, what are we going to do? Well, they say you can always turn every one of these shared memory processes into an asynchronous message passing process, where instead of sharing this memory, you imagine the memory or the critical section is another process sitting there, and you're just talking to it. So we said, okay, we'll do that. We'll rewrite this protocol using asynchronous message passing. And we told them we were going to do this. And they gave us a funny look, like, oh yeah? So yeah, sure, this will be cool. And then we can, then we'll use our protocol. Well, it took a month for us to realize that this is really, really hard. So first, the student, Jason Wu, was very happy. He was eager to go out there and do it. So he comes back with his first version of the protocol. Vincent, his first guy to look at it, finds a bug, sends him back. After about the 5th time Jason comes back with bugs, he gives up. He says, all right, Vincent, you're going to have to help me with this. So he and Vincent start working on it together for a week. And then they come to Mark. Next there, they go to Mark and they say, we can't seem to get this. Would you help us? So he takes a couple days off of what he's doing, and they work on this protocol. They can't get it. So then they go to Robert, the world expert. They said, okay, Robert, how do you said we could write this thing. How do we write it? He said, well, I said, you guys can write it. I'm not going to try to write this. It's too hard. You won't be able to get it right. So what kind of an answer is that? But he says to us something really neat. He said, there is a protocol for simulating any shared memory algorithm on an asynchronous system. So if you guys figure out that theorem and implement it, then you'll be able to get an algorithm out. Now, for logicians, this is perfect, right? This is exactly what you want to do. You want to get a general theorem that says this can be done. Prove the general theorem and then apply it to this algorithm that none of us could get. So that's what we have been doing here. And indeed, that process looks like it's going to work. I think we will finally, after several months, be able to now invoke this theorem that says, given any shared memory model and any protocol running on it, you can transform it into one that runs in the asynchronous message environment. And if you've got a proof in the shared memory thing, you can convert the proof. So that is the cool thing we want to do, given that we've been unable to do the proof any other way. And that tells you something else about this area. I mean, it's much harder to reason about than you might guess. Okay, so we're building this kind of formal transformation. How am I doing? Did anybody watch the time? I forgot when I started. Oh, okay. So I'll be good. I'll get through the talk. All right, so now let's go. So that tells you a kind of logic story. I think this ends with something that we find very promising. So we're implementing this general transformation. We're going to write the proofs in the way that you all understood, and then the machine, New Pearl, is going to convert them to the asynchronous thing that we were not able to convince ourselves was correct. Okay, but now, this was all a warm-up on shared memory. The stuff we've been working on before is in a much more complicated region of dealing with fault-tolerant consensus protocols. So the things that these guys writing cloud systems have to deal with is process failure and what they call fault-tolerant consensus. So let's see what's going on there. So all the modern distributed systems used to maintain the databases at companies like Google, Microsoft, Amazon, all of them use consensus for the following reason. They need to replicate their data. Google would be very unhappy if all of a sudden they lost power at their one and only center and all the data, all their Gmail, everything disappeared. So they have like many centers, right? And so the way they protect against anything happening at one of them is they replicate these centers. And then within the centers, they replicate sub-processes, like their Chubby system. Their Chubby replicator maintains their basic file system for the company. Okay, so this is a very critical protocol. How does Google make sure it's correct? Do they verify it? No. They have a simpler way. They pick the best programmer in the company, in this case Mike Burrows. They say, it's your job to write this protocol. We pay you a lot of money. We don't want it to ever fail. So he says, okay. And of course, he doesn't let anyone else touch that protocol. Someone comes in and says, oh, I got a great idea. We can speed this up by 5%. You can't touch it. Burrows is the only one. Well, that actually, they changed it for some reason, and we were the first guys to discover. They changed it. They let somebody else, and I won't name the person. We know who it was. He was very proud that he could now touch it. He touched it and wrote a little note about it, and we were reading this note, and we said, that can't be right. He couldn't have made that fix. So we wrote back to them and said, are you sure that you really did the right thing? And then they wrote back and said, thank you very much. Maybe only Mike Burrows can touch this from now on. So anyway, this is big business. And Facebook has already had problems where their replication has gone down. They've taken all kinds of pains to bring the system back up and not lose things. Okay, so critical protocols, they're critical because of failures. So the protocols that try to maintain the replicated databases must also respond to the possibility that they will fail. So you've got two levels of failure, right? There can be massive failure of the equipment that's maintaining the file system, but it's also possible that the protocols that are trying to keep all the replicas consistent might fail. So you have to deal with what they call fault-tolerant consensus protocols. So let's see how they work. Let's suppose we have just 3 processes who are in charge of maintaining the consistency of the replicas. So what happens is a message comes into the Google file system that says delete so-and-so's account, and before they delete it, they make sure all 3 of these managers of the database agree. That's what we should do. Go delete that guy's account. When they all agree, then they execute that delete. But how do they agree? They send messages back and forth to each other, trying to reach consensus. Generally, it goes pretty fast because they do it by this process called Paxos that picks one of these guys to be a leader. So one of those 3 processes is the leader, and all the messages go in to the leader. But sometimes the leader gets overwhelmed and it's slow, and the clients decide they need to know who to go to next, so the next one of those is also able to talk to the clients. So maybe traffic for a while is all going into number 1 there, and it's processing just fine, but then there's too much traffic, so messages now come in to 2 saying, I'm not getting a response from 1, I want you to delete that user account. So now they have to agree. Before they're going to delete the account, they ask each other, what do you think? Are you ready? Are you going to delete that account? Is the account there? So these protocols are done by message passing. They're asynchronous. But in the logic of events, it's pretty easy now to start saying what these real protocols do. Now, unlike the first ones I showed you, that trivial 2-phase handshake there, this is a real spec of the consensus protocols, and here are the properties that you have to guarantee. So for example, if all the inputs to the replicas are unanimous, if everybody says, yes, let's delete that account, then they're going to do it. And you want to know that as a spec, so you say, okay, if all the values t that come in, or for any value that comes in, if every event at the input to those managers has the same value, so here you can see E is an input event to the consensus protocol, the value of that event is V, the same one, then it better be, then it implies that all the decide events, where they decide what to write, should decide V, right? That's a basic property, and it's called something like validity. You only, that's part of validity, that you, if everybody agrees, you do it. But there's another important property that is called validity. Anything you decide should be a value that was proposed. You can't just go make up a value. Say, let's delete Benjamin's account. Everybody could say, well, it's going to be Pierce. We'll always delete his account. We all agree on that. That's not fair, because you should only be able to delete the request. So this says, for every event that's decided, there has to exist an event E prime that came before that decide event where you had a request, where that's what you were supposed to decide. So you can't just make up something. You have to decide an event where there was a request to do that. Okay, so those are good properties. But now what would you like to say? You'd like to say, all right, you'll get the requests, you'll only decide on things that were requested, and you will decide. You will eventually do this. Unfortunately, you can't decide that because there's a famous theorem, which I'll talk about in a minute, that says you cannot achieve consensus when it's possible that one of the processes may fail. And that's why this algorithm is being written, because one of the processes can fail. So, let me see, we've got to skip along faster here. So I won't have to tell you that. Okay, so the way these fault-tolerant protocols work is they set a threshold of failure. They say, well, we're going to work correctly as long as only half of the processes fail, or a third, or a quarter of them. So you pick a number, and it's usually called the failure number, F, and you say, we'll tolerate F failures. And typically, they tolerate 2 out of 5 in these big data centers. Okay, so the way they then do the voting is they send out the request for an action, delete so-and-so's account, and they send it to all 5 replicas. And if they get back 3 responses there that say, yes, that's what we're going to do, they do it. But it can happen, and it does happen, that I'll have to skip a lot of this. So here's what can happen. Let's look at a protocol like this where we've got 4 guys trying to decide, and they're getting inputs 0, 0, and 1, and 1. But the inputs are coming at different times, at different rates. So it might happen that 2 of these processes decide, yes, we're going to write 0. And the only other one they're getting the vote from is this guy with a 1, so they think, yes, okay, that's what we're going to do. We're going to vote for 1. And then on the next round, the 1 votes get slowed down for some reason, and the 0 votes, the one that we didn't see, the one that we saw and that was coming in, and one we didn't see before come in, and now the majority looks like it could be 0, and it might go that way. It might go to 0. And you can show, there's a famous theorem about this, that the processes can waffle forever. They can just go back and forth, not being able to pick a majority depending on which processes are slow. Okay, so let me get right down to the interesting theoretical result about all this. So there's a famous theorem about these distributed protocols called the Fisher-Lynch-Patterson theorem that says if it's possible for one of the processes to fail in a consensus procedure like this, then it might happen that you never reach consensus. So the theorems all have to say something like this. If at most F processes fail, then we can reach consensus. And when we do reach consensus, it'll be on one of the values that was proposed, and we'll decide only one value. Okay, so now, I'll get through this part of the story here, and we'll see how it's going. So here's the setting in which we're working then. We know we can't actually achieve a consensus protocol that always works. We have to count on the fact that not too many processes will fail. But something very weird came up in the verification of this. We discovered, working with real protocols now, that they don't worry first about this issue of whether things are going to converge. They worry about something much worse, which is called blocking. The protocols that are voting in rounds like this can get wedged if they're sitting there. They're not waiting for failed processes, but they can get into a set of states that are just going back and forth, and they can't get out of them. So they get blocked. They can never reach a consensus state. So the first thing these guys prove about all their protocols is that they do not block. They never get wedged. And when we started to prove this, we had to do it constructively. So we were proving constructive non-blocking. The other thing they talk about is this Fisher-Lynch-Patterson theorem. They're saying, we can't try for too much, so let's just go with what we've got. We'll just try to keep running and not block and hope we reach consensus. Well, what I realized by listening to these guys, I wasn't too much into trying to help them get Paxos worked out, but I was in on all the sessions, and I realized we were in more trouble than we thought here, because I went and read the Fisher-Lynch-Patterson theorem because they were citing it so many times, and in there they had a very non-constructive proof that shows the protocol could go on forever. But I noticed that if you constructively proved the protocol correct the way we were doing it, I could turn their proof into a constructive proof that would actually show you how to keep the protocol from deciding. So we go through all this effort to prove the protocol is correct, to prove it's non-blocking, to do it constructively, and what comes out of it is a perfect attacker. Because you tell the world, here's what you do to keep the protocol from converging. You just run this non-blocking thing and run the proof I gave, and that little attacker will stop the protocol from converging. And we've run this. We've watched it happen. The protocol is trying to converge. If one more value, one more zero comes in, they're going to say, yep, it's zero, let's vote. You slow down the zero channel. You say, don't let zero arrive. Let one arrive, and then they're going to go back to waffling. So if you've got this proof of the constructive Fisher-Lynch-Patterson theorem, and you're in the data center, you've got control of the data center, you can create a denial of service attack that cannot be defeated. And this was not what the guys who were funding us wanted to hear. That by verifying the protocol, you actually create an undefeatable denial of service attack. So we had to have an answer back to them. They said, we're paying you guys to actually make sure the center doesn't get taken down. But a good thing came out of this, because yes, so you have to recognize verification isn't going to do the job. Maybe when you verify, you're actually going to, well, I don't think this happens very often, create another vulnerability. But what we did discover is that because we're doing our protocol proofs at a very high level, we're doing them at the level of proofs, and then we synthesize them, we could dream up at the level of proofs several different proofs of the protocol. It was easy. Everybody who was doing this had a different opinion of how the proof should go. So here, instead of doing one formal proof like the tree I showed you before, you've got 4 or 5 people who think different ways of doing the proof should be used. So we could then take each one of those proofs and synthesize a protocol from it. So instead of getting one consensus protocol, we could get 5 or 10, depending on how creative we were at the time. Then what happened is, once NuPearl's got the protocols, that has to go through our internal compiler. And then we give it to the various compilers that are being used in the data center, Erlang, Java, and so forth. So we noticed that, okay, we can keep adding diversity. So we'll take the 5 different proofs, and we'll make the compiler do something different for, compile it, say, 10 different ways. Instead of using a list, we'll use a doubly linked list, we'll use a tree, we'll use this data structure, that data structure. So we started generating for them lots of diversity and gave them not just one protocol, but in the end we could give them around 200 provably correct protocols. So we said, all right, let them attack one of these things. We've set up the system so that it can, if it thinks it's under attack, it can swap protocols. But the way we're using it now is we just keep changing the protocols. So nobody is ever going to know what we're running at any given moment. We can get this easily up to 1,000 variants, and we can do them randomly. So this kept DARPA happy. You don't want them to think formal methods guys are only going to give you headaches. This technique turns out to be very effective. And we've already got that running in this little shadow DB where we can diversify the kinds of protocols that we create. But notice, you can't do this. This takes formal methods. This takes a logic of events. This takes proofs. Because you can't just swap in protocols that might be correct, right? You've got one that's correct, and you decide to swap in something else. Everything we swap in is provably correct. So as we change around from one to the other, we're not ruining the correctness of the system. But we are keeping the attackers and anybody, an inside attacker, from being able to take down the system. Okay, so anyway, I thought that was a cool story, and they call these protocols now attack-tolerant protocols. This is a new field of study called not just fault-tolerant protocols, but this field of study, attack-tolerant protocols, depends on us, on you guys. You can't do it unless you verify these protocols. So I hope this easy lecture, I told you it was mostly stories and all that, but you can see underneath this is a lot of potential for us to be in there trying to verify other protocols by this logic of events, and to make sure the logic of events is really covering the world as it is. And let me tell you my hunch about that. These protocols are not like computable functions. They are very much unlike a Turing machine, right? So the systems you're dealing with in distributed computing are much more like Brouwer's idea of free choice sequences coming, because you're always having to deal with the environment. You've got your players that are running on computers, but the environment is not a computational player. Who knows why the channels get slow? Who knows why all of a sudden the traffic between two nodes drops down to almost zero? What happened? They don't know. These guys, our systems group monitors the networks all the time, and they try to figure this out, and that's why they tell us it's quantum mechanics. Nobody can tell which links are good, which links are bad, why they're going down. So that is what our computing theory has to deal with. In the logic of events, the primary thing is going to be two players, the environment and the computers. And the environment is not a Turing machine. It is what Brouwer said it was. Brouwer said you're going to have to deal with free choices. He was thinking of creative minds, but that's essentially what we've got. Creative minds have made this very unknowable computing environment. So I predict that this logic of events is not going to look like temporal logic or anything else. It's going to have an element of fundamental intuitionistic logic in it that will be unavoidable. My colleague Joe Halpern, who loves to think about logic puzzles, hates this idea with a passion, says it can't be true. But he knows that the way he proves protocols correct can't be the way it can't translate into what the protocols know. Anybody who does it classically, by the way, they just say, I know the state of the world. Here's a cut through all the events. Here's what happens. Here's what the protocols can do. Those protocols are never going to be constructively verified, because the agents, what those protocols are doing, depends only on the messages they get. They have no knowledge of the global state. It's like this magic thing. Those protocols cannot know the global state. They are like we are. And Brouwer said we are constructive proof engines. So I predict that when we get to the cloud and we're proving all this stuff correct, it's going to be constructive type theory that they use to prove it, because the classical theory just isn't going to make sense in this setting. So anyway, that's a vision for the next 10 years.